2:30. No, it's right in the middle of winter break, so not many people are around. So that's why I've asked the math department to record this talk. It's a very wonderful choice to have expert in polynomial system solving tropical geometry, and also because of my personal schedule. So unfortunately, we have to schedule the talk during this week when there are not so many people around. But still, but we have the talk recorded, so I'm going to make it available to other graduate students after the break. Jensen is an expert in from Aarhus University. He's expert in tropical geometry. He's going to talk about tropical geometry, polynomial system solving. So, please start.
Thanks for the introduction. Yes, so I'll start by talking about the basic object in tropical geometry, and that's the tropical semi-ring. So we look at the following ring T. We let it be the real numbers, and then we add in infinity, and then we consider two tropical operations, the tropical plus and the tropical times. So this is a semi-ring. And what is the tropical addition? Well, that should just be minimum. And what is the tropical times? That should just be sum. So as an example, we can do the following computation in tropical geometry. 7 times 2 plus 3. What is that equal to? Well, 2 plus 3, that's equal to 2, because I should take the minimum. So it's 7 times 2, and tropical product was just the sum, so this is 9. But then we notice that it's also equal to something else. It's also equal to 7 times 2 plus 7 times 3. Right. So it's a bit surprising, actually, the distributive law holds here. Because this is 9 and this is 10. So the minimum is 9. But that's what makes tropical geometry interesting. The next thing to consider is tropical polynomials. So I'm going to write out a tropical polynomial P. It's going to have 3 terms, and the coefficient of the first term is -1. And then the monomial part is x times x, and then we add 0 times x, and then we add the constant, which is 2. So here's a tropical polynomial. Let's try to draw its graph. When we draw the graph of a tropical polynomial, we should first notice that actually in usual arithmetic, what is this? This is x plus -1. So usually we would write it as 2x minus 1. And what about this over here? Well, that's just x plus 0. So we would just write it as x. And the 2 is just the constant 2. And now we are supposed to take the minimum of these 3 functions. So let's draw the graph of the 3 functions. Suppose 2 is up here, and x is here, and then the last one, 2x minus 1, must be something like this, right? So the minimum is this function. So the graph of the minimum is like that. So that's That's a tropical parabola. And now this thing, we would like it to have two roots. So what should the two roots be? And if you make enough examples, then you realize that probably a good choice is to take the roots to be these two choices of x, namely 1 and 2. And why is that? That's because in these points the minimum is attained twice. So that's the break point. And there's going to be degree many of those if we count with the proper definition of multiplicity. So we define the roots of P to be the set of x into R for which Px attains the minimum at least twice. So we can check that if I take the number 1 and I try to evaluate these three functions, then I get a 1 here, and I get a 1 here and a 2 here, and so the minimum is attained twice. So that's the tropical polynomial, and that's the tropical roots. So now we may wonder, why do we consider this at all, and what is the connection to the usual polynomials? Well, it turns out that the connection is through Puiseux series. So let's recall that a Puiseux series is, well, the field of Puiseux series is written like this, and what is that? That's power series in T with rational exponents. And then some other condition about the denominators of those exponents. Well, there should be a common denominator of those exponents. This turns out to be a good field to consider, and let's consider now a polynomial over this field. So I can write out the polynomial t minus 1 times x squared plus x minus t squared. So this is a polynomial in x with coefficients in the Puiseux series. And maybe I will call this polynomial f. And now let's try to find the roots of this polynomial. Well, it turns out that we need to make a good choice of an first exponent of t. For example, if we said that the series should look something like this, what will happen? Let's see, if we substitute in this for x, then we'll get degree here, we'll get degree 1 here, we're going to get degree 1 here, and then that has degree 2. So if we want the lowest degrees to cancel, then we should be careful about picking the coefficient. And it turns out that if we pick a minus 1 as coefficient, then things will cancel here in the first degree. But in the first degree. So a root of this polynomial is going to look something like this, and then some higher order terms. But there's no other choice of exponent for t. We could also have chosen t squared. Because what happens if we put in a t squared here, then we get degree 4, but then we multiply by t inverse, that gives degree 3, so we get degree 3 here. Here we get degree 2, and here we get degree 2. So you see that the choice of coefficient +1 actually makes degree 2, the degree 2 terms cancel. But then in degree 3 we're going to get problems, so we need to add in some higher order terms. So, so roots look like that, and the claim is that the possible exponents for t came from dt, where p is the polynomial that was over here, the tropical polynomial. Because 2x minus 1, that's actually the degree of this if x has degree x. So we call T the tropicalization of f. So let's just so write P is equal to top f, and let's just consider what happens when we pass from f to its tropicalization. Well, we're going to replace usual multiplication by tropical multiplication, and then something happens to the coefficient. Instead of taking t to the power minus 1, we're going to take the exponent there and put it as coefficient. Then same thing happens here. The exponent here is 0, and over here the exponent is 2. We throw away the minus. Actually, what we are doing to the coefficient is that we are taking valuation in the persistence. So that's tropicalization. So this leads us to the first example of how tropical geometry is useful for polynomial system solving. And that's the Newton-Puiseux algorithm. So what is the Newton-Puiseux algorithm? Well, the Newton-Puiseux algorithm takes an input, and that's a polynomial with coefficients in the Puiseux series, and then it takes some exponent from t top f, and then it also takes an n natural number, and the output is going to be what? It's going to be the first n terms of root x of f with exponent with small t exponent equal to that omega that was input. Right? So the algorithm is going to take a polynomial, say that polynomial, and then one of these exponent choices, and then it's going to produce as many terms as I would like from the root. So what are the steps in the algorithm? Well, what I'm going to write now is not how you would usually present the algorithm, but if I want to use the tropical terms that you just had, then the steps in the algorithm would be like this. So the first thing is to find a suitable coefficients, let's say C, complex coefficients for T omega. Right? That's what we did before. We needed to pick a coefficient here. Here we could pick -1 and 1. So we want things to cancel in the right degree. And when we've done that, then the next step is to substitute. And we're going to make the substitution that x is going to be equal to C times T omega plus y. And do the substitution in f and get a new polynomial that we'll call f prime. And then what do we do to get the second term? Now we need to figure out what y should be to make y a root of f prime, because that would make x a root of f. So we compute an omega prime in T top f prime, and then compute the n-1 terms of a root of that new polynomial f prime, and then with the regulation with the exponent being omega prime. The exponent omega prime, and this happens recursively. Right, so I've written out this as a recursive algorithm. So we figure out what the first coefficient should be, figure out what the next exponent should be, and then we call the algorithm to get the following exponent. So if you want to find roots of a single polynomial over the Poisson series, then you would use the Newton series. The next thing I'm going to do is I'm going to introduce more variables. But I will not make it too complicated, because now I'm going to first consider linear polynomials. So I'm going to tell you what a tropical line is. So to figure out what that is, I'll start by writing up some linear polynomial. So let's choose the polynomial to be 2 times x plus 3 times y plus 4. So the idea would be that such a linear thing should define a line. And I'm still interested in figuring out for what choices the minimum is attained twice. So I'm going to define T of P to be the set of x comma y in R2, for which P xy is attained at least twice. How to figure out what choices would work here? It turns out that the easiest way to do this is to first figure out what choice of x and y makes all terms equal. So if we choose 2 and 1 as x and y, then we see that this term becomes 2 plus 2, which is 4. This becomes 3 plus 1, which is 4, and the last one is 4. And so if you make this choice, then the minimum is attained by 3 terms. Right. So that the minimum would be attained 3 times. So let's try to make a picture here. So 2, 1. That's the point out here somewhere. Now, what happens if we make x bigger? Well, x becomes bigger, then this will no longer be 4, but these two numbers will still be 4. Right? So if I go this way, the minimum is attained 2 times. Similarly, I could go from this point and make y bigger, then this would still be 4, and this would still be 4, but now this would be more than 4. But the minimum would still be attained twice. Another thing I could do was to lower x and y simultaneously. Like for example, I could put x equal to, well, if I make x1 less, then I'll get a 3 here, and if I, how do I say this? Oh yeah, if I make y1 less, then I also get a 3 here. So I could also go down this half line. So what I've drawn here is TP. This is a tropical line. So I can get other tropical lines by changing the coefficients. So let's draw some tropical lines here. If I change the coefficients, then I can get things shifted around, but it's still the same picture. So this is one tropical line. Let's try to draw another random tropical line. And what's the funny thing here? The funny thing is that the two random tropical lines intersect in one point. And that works even if we had placed this tropical line over here. It doesn't always work. I need to be like random. With probability 1, I'm going to place it so that there's an intersection, so that there's a unique intersection point. If I could also place them on top of each other, then it would not work. But with probability 1, we're going to get a unique intersection point. Another funny thing is that if I now take two random points, then there is a unique line that passes through them. So there are some things that are very familiar to us that survives when we go to tropical geometry. Let's make things more complicated. I will now go to degree 2. So I'll write up a polynomial. I'm going to take p to be 0 plus minus 1 times x plus minus 2 times y plus minus 3 times x plus minus 3 times y, and then the last term minus 2 times x times y. So imagine that we had 6 linear functions, and we're going to take the minimum of those 6 linear functions. I'm not going to do the computation here. I will save some time and instead draw the picture of where those 6 linear things break. So where the minimum is attained twice. The picture looks like this. And I can give you coordinates for those points there. For example, 0, 1, 1, 1, 2, 2, 1, 0. So the origin must be down there. And each of the regions here then corresponds to a monomial. So this region here corresponds to the monomial 0. That's where 0 is the minimum. And this region here is -2 times x, and this is -2 times x times y, and I think this is -3 times x times x, and so on. And in between, the minimum is attained at least twice. So now here comes a theorem that I will not prove. A degree D1 tropical curve. So what do I mean when I say tropical curve? I just mean something in the plane that's given by a polynomial. And a degree D2 tropical curve intersect in D1 times D2 points. And then I should say generically, so which for this talk would just be with probability 1 if I choose randomly. And this is counting multiplicity. To make this precise, I need to introduce multiplicity, and then this is true. But I will not introduce multiplicity today because that would be too much for this talk. Counting multiplicity. So let's just make an example. Imagine that this was 1 degree 2 curve, then maybe I could make a similar curve down here. That would look something like this. Right, and you see that they intersect in 2 times 2 points. And if we slide things around, then that still holds. For example, if this line was then the cross here, then the intersection point would go from here to down here. So this is also how things usually work. If I take some random algebraic curves in the plane, then I would also get this intersection. But when I say random here, or generically, I really mean that all the terms appear, right? All 6 terms of degree less than or equal to 2 appear in these polynomials. We can also get a theorem that talks about what happens if some terms are left out. Yeah. But maybe before I say that, in general, what is a tropical hypersurface? A tropical hypersurface is such a TP of a tropical polynomial. That's what I would call a tropical hypersurface. So over here, we have 2 tropical hypersurfaces in the plane that intersect in 4 points. I'm going to use the word tropical hypersurface later in the talk. So what if not all coefficients are there? Well, then there is a tropical BKK theorem. And what does it say? It says for invariant random tropical polynomials, and we have that the number of intersection points in the tropical hypersurfaces if there are n of those, is going to be equal to the mixed volume of the Newton polytopes of the polynomials. Now, I did not define what a Newton polytope of a polynomial is. I also did not define what a mixed volume is, but it has something to do with volume. Something to do with volume of polytopes, so you can get the number of intersection points by computing some volumes of some polytopes. This is the tropical BKK theorem. What is the classical BKK theorem? Well, the classical BKK theorem is a theorem from 1975, I believe, and the B is Bernstein. What do we have? Kuznenko and Kowalski.
Bernstein.
What?
Yeah, Bernstein.
Yeah. And Bernstein's paper is from 1975. And what does it say? It says for random polynomials, f1 up to fm, so fn, and let's assume that this polynomial is over our persistent field. We have n variables. Then the number of solution points, the number of common roots of f1 up to fn is equal to the mixed volume of the Newton polytopes of f1 up to Newton polytope of fn. So that's also a bit surprising. The reason that I mentioned this here is that, well, there are several reasons. So note the following. First thing to note is that mixed volume is best computed using tropical geometry. And there's some complexity results about this. Well, yeah. Then another thing is that there's something called polyhedral homotopy continuation. And this is by Huber and Stufels and Versierde and others. And what about polyhedral homotopy continuation? Well, polyhedral homotopy continuation makes this theorem constructive. So there is a way to there is a way to set up what's called a homotopy between solutions of one polynomial system to a system of another polynomial system that will like track mixed volume number of solutions as we change the system. In that way, this EKK theorem becomes constructed, so we can find the solution. And the first step in this process would be to compute intersection of tropical hypersurfaces. So that's an odd connection to polynomial systems. So now I'll talk about why there is a connection, or what the connection is between the classical world and the tropical world. So I want first to mention that there is this thing called evaluation that goes from the field of precise series, and I'm going to remove 0 from the precise series, so put a star here, into the rational numbers. What does the evaluation do? It takes the precise series, then takes the first exponent that appears. That's the evaluation. Now we can apply such evaluation coordinate-wise. So if I now have a vector of precise series, then I get a vector of rational numbers. Now let's take I to be an ideal in the polynomial ring or the precise series. Well, then what can I do? Then we can look at the usual variety, and I should throw away the 0, so if the point of 0 coordinates, I forget it, and then I can apply the evaluation map here coordinate-wise, and what I get is going to be the tropical variety of I. So I define the tropical variety of I to be what you get when you take the usual variety of I in the vector space of precise series, and then afterwards apply the evaluation at coordinate line. And that's going to be some polyhedral complex, so looking much like the curve that we've seen before, and sometimes maybe we should probably take the closure right if we want to go into IN instead of QN. Take the closure. Then we'll get pictures as we saw before, the degree 2 tropical curve, for example. And this thing, the tropical variety of I, satisfies some properties. So I'm going to list a few of them. Hang on. Maybe I'll do it over here. Properties. First property is that I could also have defined the tropical variety as an intersection of tropical hypersurfaces. Take a tropical hypersurface for any polynomial in the ideal. That's property 1. The other property is that there is an algebraic way of defining this instead. I could say T of I is the set of all omegas in Rn for which the initial ideal of I with respect to omega is monomial free. This may seem very mysterious initial idea that something that comes from Grosvenor basis. But if people do Grosvenor basis, they don't usually use a vector here, they use a term ordering. But it's related to that. The important thing is that if you use this definition, then the whole TFI becomes computable. So this thing here becomes computable. Yeah. So then another theorem, so this is usually called the fundamental theorem. Of tropical geometry. And then what else? For I prime with dimension of V of I equal to D, then the following thing holds. T of I is a pure d-dimensional balanced connected polyhedral complex. To be precise, I should say it's the support of a polyhedral complex. What do these mean? So pure d-dimensional means that any inclusion maximal phase will have dimension d, and balanced means that the tropical horizon cannot look like this. Somehow it needs to, if it goes in this direction, it also needs to go in that direction. And connected is clear. So this is sometimes called the structure theorem. The structure theorem. And then why do I say all this? That's because we should notice the following. What's that question? The dimension of VI can be bounded let's see, tropically. Well, maybe first notice that usually if I wanted to compute the dimension of V of I, that would be a Grosvenor basis computation if I was given generators for I, and that can be very difficult to get. But we can get a bound using tropical geometry for the dimension of V of I. How does that work? It works like this. You choose some set of polynomials f in the ideal, and then you say T of I by the first point up there, and then T of I sits inside intersection of T of f, where f runs through f. And yeah, so therefore if you can choose some f's so that you get the dimension of this complex to be small, then you also get a bound on the dimension of T of I. That's going to be used soon. So I'm going to talk about an application, and an application to celestial mechanics. Now there are experts in your department, but I'll just, in case people don't know what the experts are doing, I'll just spend 1 minute defining what a central configuration is. Here's the application. A central configuration of endpoints, endpoint classes. No, that's not the way to say it. It's about to write. I should say, a configuration of n-point masses is called central if acceleration points, and then I need to write proportionally to the center of mass. Right, so the example is the sun is here, a planet is here, two asteroids are here and here. They will be attracted. If they're placed correctly, then they'll be attracted to the center of mass, which will probably be somewhere here, in such a way that if we just release them, right, then everything would. So no motion to start with, then everything would collide there in the center of mass. Or the way it happens in the solar system, right, is that everything is rotating and forces cancel out. So this is an example of a central configuration with four bodies. Then there's the Smales 6 problem. It says, prove that given n masses, meaning the weights of the points, there exists only finitely many central configurations. So that's Smales 6 problem, and the problem made it to Smales 6 because it's very complicated. There was progress in 2006 by Hampton and Merkel. And they proved that it's true for n equal to 4, there can only be finitely many central configurations. And I'd like to sketch that proof, and maybe that will be the last thing I do. This doesn't exist. I think I'll sketch the proof. So the first thing is that we should think of the masses as being unknown. And somehow the argument that you do should work for these masses anyway. And here is a tropical interpretation of their proof. Here's a tropical sketch. And at the time they did the proof, all this terminology, the tropical terminology, was developing. So they didn't use the tropical terminology, but for me it's easier to phrase their proof in tropical sense. So what is it they want to prove? They want to prove that it turns out that what one wants to prove is that a certain polynomial system has only finitely many solutions. So this is the solution set, and one wants to prove that it's finite. And they want to do that over the real numbers, actually over the positive numbers, and the way to think about the space here is that this is the space of pairwise distances. So for four bodies, this would have dimension 60. They want to prove this. How do they prove that? Well, they say that it's enough if we can prove that this thing is finite, even if we so this is finite if we consider the larger field of precision series. But then from algebraic geometry we know that that's the same as saying that this set here has dimension 0. That's how algebraic geometry works. But now, from the theorem that we have up here, the dimension was preserved when tropicalizing. So therefore we can also just prove that the dimension of T of this idea is 1 up to Fm is 0. But then we can use more properties of tropical geometry. Namely, if one uses this balancing property, saying that a tropical writer cannot point in one direction without pointing in the other direction, but cannot point in one half space without pointing in another half space, then it's enough to show something else, namely that the dimension of T of the ideal generated by F1 up to Fm intersected with a half space the dimension of that is 0. And what is then the argument? Well, what do they do in the paper? Phrased tropically. Tropically, they will compute the larger complex T of F1 intersect up to T of Fm. So this is larger than this one. And now we can look at all the cones, right? This gets like a structure of a polyhedral complex, so we can talk about all the cones that sit inside this, and we can check each of them and check does it really belong to T of I, or I should intersect H the half space too. So then they rule out cones algebraically using this characterization there. So that means that they check that each cone that's not just the origin contains a monomial. So each cone contains a monomial. So that's how to trace the argument property. And then there's still a little time left. So maybe I'll tell you what the story is besides this. So for 4 bodies, the problem has been settled. Smails, the answer is yes. So now the question is what happens for 5 bodies. And for 5 bodies, then there's the F1 correlation result in 2012, and they say that it's true except possibly these cases, and then they come with a long list of possible exceptions. These are conditions on the masses where the result is not known. Let's see then what else. Actually, this is the planar case. One can also look at the spatial case. That's not part of Smail's problem, but still you can ask the same question. For the special case, I together with Hanson proved a similar, basically a similar result for as in the planar case, but yeah, with different exceptional cases. And then let's see. Now, what can one do? One can then go to and ask the question about six bodies. And two people in our audience are now trying to see if they can get this result for six bodies. And at the same time, I'm trying to gather with, maybe I should put this before, B and some Laken, we had a result that kind of does the same thing as the Colossian result using different tropical arguments. Here, unfortunately, we do not get the long list of exceptional cases, but we get the short version of this story, namely that for generic choices of masses, then the conjecture is true. And now, so now we are competing with the six bodies case who may come to a result first. And now I think I'm running out of time. Let's see. So the trick in this Jensen result that works for 5 bodies but not 6 is to choose variations on the masses m1 up to m5, and then try to argue about all those masses with these variations at the same time. And then one can compute a polyhedral complex and show with a similar kind of argument that it only points in one direction. And then one says that, oh, but this set of masses that which shows, that's Zariski dense inside the set of all masses, and therefore generically the finiteness is solved. I think this would be the end of Thank you. Thank you for listening.
Thank you. Any questions? Oh, I do have questions. I have many questions. So maybe too many. I'm thinking about maybe we can talk about this in the next hour or two. Yeah. So, about the approach Hampton-Markov, they actually their original system using the Albi-Chesney equation are not good. They have to add another 4 polynomial equations.
Okay.
But still, you calculate the Newton-Polytop and do this kind of reduced system for the Minkowski sum polytop and do a lot of these things. Can you say something like what makes the tropical approach better? Or because there are actually many complicated cases to deal with. There are 8,000 phases.
And one thing is software here, right? Because the way that they do the computation is they do what they call the big Minkowski. They have computed big Minkowski sum of many.
You don't need to do that.
Phases. I don't need to do this. I'm like keeping track of which of these phases on the Minkowski sum actually has a chance of contributing to the final result. So they like do a big computation, and afterwards they rule out phases as far as I can understand. I'm more careful about this.
So maybe that's the reason why, because I used to have the impression that if we just follow their approach for the 6-body cases, for the 5-body cases, seems impossible.
Yeah, because if you do that computation, that's going to be huge. Yeah. That's what you want to try to avoid all the. But yeah, actually, you don't want to know all the vertices of that polytope. You want to know very particular. Okay.
Well, how about the finiteness part? Like the finiteness part, what they did is that they have to look at each facet corresponding to each facet as a reduced system, and make sure that if there's only trivial Pursue series solution, then you can rule out that face. For this part, does it correspond to which part in your?
So that system is the initial. Well, almost. You take in what's in this setting called initial forms of your original system, and yes, that system called the reduced system would be what I would call initial forms of the original. Yeah, so mainly it's just a language problem, but for the thing about computing the intersection of probable hypersurfaces, it really is much easier to think of it in terms of hypersurfaces.
When you apply your method to the 5-body case, you use the Aubrey transformation equation, right? Instead of Aubrey college.
Yes. Yes. And some other equations now that I don't remember exactly.
Have you tried using the formulation of the Aubrey collation? Does that work better or worse?
We didn't get very far. I think that's what. It didn't work out as well. And is there any maybe intuitive explanation? No, wait. No, I'm mixing things up. No, we cannot use the Edward ecology for the spatial case because the coordinate is points in the complex thing.
You mean the non-planar case, non-planar case, right?
In the non-planar case, we cannot use.
Right.
So
that's more planar.
But down here, we also try with
That's for the 5-body. You mentioned you work with Hampton, the 5-body spatial case. That's still back.
Right, but we get the equations. I mean the exceptional. We get the exceptional cases. The result follows from the numerical result. Yeah. So actually, this was known. Generic. Yeah. The generic finiteness was known.
Yes.
By
Merkel. Yeah.
Yeah. But we get the equations now.
Even for the.
I mean the exception we get. Yeah, just as they have this stuff. I don't think they write out all these exceptional cases in that paper. But in our paper we have like a.
You have to rule out all possibilities,
but we have the list, and I think it fits on the page.
Okay.
Yeah.
So all of them, not just generic methods. Is that right?
Yeah, but we haven't ruled them out.
Okay.
They're still listed.
Okay. Still listed as exceptional case.
As exceptional case.
All right. So sorry, I should not take too much time. The recording is for 1 hour, and if you have any questions now? If no, then you are welcome to stay and discuss. We can talk. The Anderson is going to stay here during this week, so we can have more time to discuss. Let's thank Professor Jensen again.